Alrighty. Hi everyone, my name is Marcello Bisicchia, and I will be presenting the preliminary design review for Aqua Alert, developed by Team Meatball. So Aqua Alert is a real-time water quality monitoring system designed to detect unsafe water conditions and notify stakeholders quickly and reliably. So in this presentation, I'll walk through our mission, our system architecture, preliminary design, prototype results, verification approach, and risk assessment. So here are our team roles. So our team consists of 5 members, each with defined system engineering roles. So there's our team there. You can view that. And then moving on is our mission and problem statement. So our main problem is that we have unsafe water conditions, and those conditions are going undetected for too long. So our environment is experiencing these unsafe water conditions. People are using unsafe water, and so current water quality monitoring is often manual, it's delayed, it's reactive, and it simply does not work. And so Aqua Alert provides a solution for that. So the mission of Aqua Alert is to autonomously monitor water quality and protect public health by providing timely and reliable alerts. So our system continuously measures pH and turbidity. It will detect unsafe conditions in real time. It'll notify city public works and the public quickly when thresholds are exceeded, and much more as well. So the problem and stakeholder needs. So the core problem we're addressing is that current water quality monitoring is often manual, it's reactive, and it's delayed, as I mentioned before. So unsafe conditions may go undetected for longer periods, and public access to real-time data is limited. So our primary stakeholders include the city public works, local communities and residents, such as schools, as well as environmental organizations, all of whom will benefit from faster detection and better visibility into water quality for their area. Based on our stakeholder needs and our system objectives, our objectives are to continuously measure pH and turbidity, and then therefore detect threshold violations quickly, provide timely alerts, maintain high uptime and reliability, as well as operate autonomously with minimal user interaction. So here's our system and subsystem architecture. So the diagram here shows the overall system and subsystem architecture. At the edges, you will have a floating sensor buoy that collects pH and turbidity data. And that data is then transmitted wirelessly to a cloud processing hub, where it is then aggregated, analyzed, checked for threshold violations or anomalies, things like that. Then, based on that data, alerts are then generated and sent through our alert engine. While all data is visualized through a dashboard UI and stored in the data storage subsystem for long-term access, and compliance, basically logging all the data that it would collect over a long period of time. And so our preliminary design rationale. So our preliminary design centers around a floating buoy platform. So this will allow for continuous monitoring while keeping sensitive electronics protected above water, because water could damage, of course, all those electronics we're dealing with. So sensors remain submerged. A visual indicator provides immediate local awareness, and then a cloud plus mesh network ensures reliable data delivery even during connectivity issues and things like that we'll get into a little bit later. And so our core components. So the core system components include pH and turbidity sensors. It will include a waterproof buoy enclosure, an onboard processor with local storage to store all the data, wireless communication for cloud and mesh networking, as well as an indicator light and user dashboard for alerts and visualizations and things like that. And so here are our performance expectations. So from a performance standpoint, we expect accurate and frequent measurements, reliable alerts during unsafe conditions, data retention during network outages, and continuous multi-day autonomous operation. And going on to our prototype overview. So here would be a quick picture of our prototype and going more into depth with it. So this is a working prototype that we made through MATLAB, and this is a quick snapshot at what the dashboard interface would look like. So the buoy model, pictured there on the left, demonstrates how the system would be deployed in water, for example. So while the dashboard shows more real-time and historical data visualization for the pH and turbidity levels. So we tested the system under safe, moderate, and dangerous conditions, and the dashboard clearly reflects these states through trends, through different thresholds and alert indicators. And so this prototype, in a way, validates that our end-to-end data pipeline from sensing to visualization is a real feasible at the PDR stage. So here you can see it, different trends and things like that, sensing data such as pH level over a certain period of time. So in this case, it would be 1 month, so 30 days. And you can export the data, and it will give you all the information through that entire time period, even with certain outages and things like that with data storing. Here's a more in-depth overview of what the user could kind of see throughout the dashboard. They'll be able to pretty much see all the data. So any stakeholder will be able to come in here and check kind of like what the sensors are reading and how they're working. Certain stakeholders that would have like maintenance with the end system would be able to see a little bit more than just like the public person, but this is a kind of an idea of what it would look like in this stage. All right, so verification and validation. So this was our approach. So to verify and validate the system, we mapped each requirement to a specific verification method, including test, analysis, inspection, and demonstration. So for example, the timing requirements are verified through testing, and accuracy requirements through certain analysis. The environmental requirements like flotation and waterproofing would be validated through demonstration. And then all these things, this pretty much ensures that every requirement in our RTM is measurable and verifiable. And they will be completed essentially as the project goes along. And then as the project is completed, each requirement is met. And so going more into our ConOps validation, looking at certain scenarios where the system has to get through. So we validated our system against several different ConOps scenarios, mainly including storm runoff events and connectivity outages. Those were the real main ones that could cause us problems. So in these cases, the system correctly detects unsafe conditions. It changes the local indicator. It'll upload alerts to the dashboard and will continually store data locally. And then when connectivity is lost, it'll do that. And then it will upload it once the connection is restored. So that's like one main example scenario there. Another is connectivity outage. So when the buoy is offline at all, if it's online, again, like what I explained before, it'll store it locally and then upload it after reconnection. And then moving into our risk assessment. So at the PDR stage, our main risks involve environmental exposure, network outages, and alert visibility. So we really mitigated these risks through waterproofing, local data buffering, redundant communication paths, and a external visual indicator to alert users, even if the dashboard is unavailable. So all risks have been assigned mitigation strategies and subsystem owners. So obviously, some risks have more weight than others, and so those ones take much higher priority. But regardless, every risk has a mitigation that we plan to tie back to certain requirements for the system. And then overall, once the system is complete, these risks should be pretty flattened out so that they're no longer risky for the system. We want to make sure they're all covered. And yeah, that is our presentation. So in summary, Aqua Alert demonstrates a complete and traceable system design supported by a working prototype and a clear verification plan. So at this stage, the system is ready to move toward detailed design and the critical design review, and of course, tracking all the requirements going through the entire process. But thank you for your time, and have a great day.